everyone, welcome to today's video. Today I wanted to start off a new series just because I personally am going to be studying for the AIGP. So I just wanted to put a disclaimer in first that first of all, I'm not a data privacy professional. Second of all, I haven't taken the AIGP exam yet. But I wanted to gather a lot of resources and repost anything I've learned, not only for my sake to be able to go back and review, but for others who find themselves in the same boat as me. A beginner, I'm not a programmer, I don't have a computer science degree, but I'm really interested in learning more about AI and how it should be governed responsibly. Because this is going to be study guide material and I'm not a professional, I am going to be referencing a lot of people who are smarter than me, and I'll link any of the sources that I use to compile this information, and I'll put them in the description below, or I'll even include clips in here like I've done today with this video. So if anything I said doesn't make sense to you today, go ahead and check them out. They will have longer videos explaining them in depth. Another disclaimer that I wanted to put in for this video in particular is that I don't believe this material is specifically going to be covered on the AIGP. Looking over the body of knowledge, there's nothing that points to you need to know the specifics of early AI and the technicality of how AI works. But as someone who doesn't have real working experience in this field, I felt it was my responsibility to learn the basics of AI and just have a foundational understanding on how it works, just so that I can better understand in the future anything that other people might be referring to. So again, think of this study guide as sort of my personal study guide and all of the materials I will be using to study for the AIGP exam. Just because from what I've seen online, either the exam materials are very expensive. When I saw that price for the exam, I almost fainted. And if they're not expensive, they're not necessarily official. So it is sort of a newer exam and not many people have taken it as I've seen online. So if you have taken it and you have relevant experience and you see something in here that I missed, definitely let me know. This is going to be helping me and then anyone else who watches the video as well. So without further ado, let's get into today's video and start discussing basic AI concepts. So what is AI? AI is described as systems or machines that mimic human intelligence to perform tasks and can iteratively improve their performance based on the information they collect. So what does it mean when we say it can mimic human intelligence? Obviously, it's not human, but it can simulate certain human behaviors like reasoning, decision-making, and planning. To do this, AI systems are often built using something called a neural network, which is a structure inspired by how the human brain works. You've probably heard it a million times before that AI can learn and it uses neural networks, but what does that actually look like? Let's move past the buzzwords and really unpack what's going on here. Let's start at looking at the brain itself. How does AI actually mimic the brain? So if you take a look on screen here, you can see a real biological neuron on top of an artificial one on the bottom. That is also known as a node. They look pretty similar, right? Now let me get someone smarter to explain how a human neuron works.
A neuron has dendrites, which receive charge. The dendrites in cell body accumulate charge until a voltage threshold is reached. Once the voltage threshold is reached, the cell fires and an action potential travels down the axon. The real computation of a neuron is done with a time-dependent integration of charge. Charge accumulates within the dendrites and cell body of the neuron. Receiving positively charged ions drives the neuron closer to the firing threshold, and receiving negatively charged ions makes it so the neuron is less likely to fire. Now, some people may look at this as a binary on or off event. However, deciding if a neuron is going to fire is decided by sending many billions of charges in a time-dependent, continuous manner, with direct interaction from the inputs controlling the output.
So as the video said, in our brains, neurons pass electrical signals between each other. Artificial neurons do something similar, but with numbers and math instead of electricity. They're connected by weights, which I'll explain in more depth soon. But for now, all you need to understand is that weights determine how much influence one node has on another. This parallel of information flowing through interconnected units is exactly what gives AI its ability to mimic certain aspects of human reasoning. The structure known as a neural network is foundational to how AI learns. But learning is more than just passing signals. So what does it actually mean for AI to learn from data? Let's shift to the second part of that AI definition, learning. The second part of the AI definition includes the idea that it can learn from data, but what does that actually mean? To iteratively improve means a system goes through repeated cycles of testing, evaluating results, and refining itself. When a program does this on its own without human input, that is considered learning. Technically speaking, learning involves automatically improving performance on a task by adjusting internal parameters called weights based on experience. The system evaluates how well it did, calculates any errors, and updates itself to reduce those errors in the future. Think of it like a feedback loop. It's kind of like a kid touching a hot stove. They do it once and then they learn not to do it again. AI does the same thing at scale with much faster processing and with vast data sets. So now that we've actually explained the concept of learning, let's see how this actually looks inside of the network. Just like human neurons send electrical signals based on strength, artificial neurons pass information to each other with weights representing the importance of that data. Let's say AI is being shown a picture of furry ears, a snout, and paws. One node might say this looks like a dog, and another might say it looks like a cat. If the signal saying dog has the stronger weight, that conclusion is more likely to be passed forward in the system. So I know this all sounds very metaphorical and abstract still, so let's bring this into something concrete. To understand how these individual pieces work together, we need to go back in time to one of the earliest building blocks of neural networks. Enter the perceptron. Perceptrons, no, not Decepticons.
Oh, brother, this guy stinks!
Were invented in 1957 by psychologist Frank Rosenblatt. Like we've already seen, a perceptron is a very simple model of an artificial neuron. It takes multiple inputs, multiplies them by weights, and adds them up. So what is a weight? A weight is a numerical value in the perceptron's activation input equation, that is a mouthful, that controls how much influence an input has on the final output. The values of these weights are not chosen manually. They start with random numbers, and the perceptron updates them during training. When the perceptron gives a wrong output, it adjusts each weight slightly to reduce the error the next time it's run. Now, mathematically, we can see how this works in a little bit more detail. When the inputs are multiplied by the weights, everything is added together and passed into something called the activation function, which decides if the perceptron should activate or not. Here's where biology and math meet again. A threshold is the minimum value that the perceptron's weighted input must reach before it activates. If the total is below the threshold, the output stays at 0, which, if you remember from the video earlier, is pretty much the same way biological neurons fire their action potential once a certain electrical threshold is reached. So how exactly does an activation function work? An activation function is a mathematical rule that takes the weighted sum of a perceptron's inputs and transforms them into an output. Now let's talk about how these perceptrons actually learned from experience. The early perceptron couldn't learn complex patterns on its own. We had to manually adjust the weights that were active for each training example by increasing or decreasing them by a fixed amount called the learning rate. This is what we describe as supervised learning, a type of machine learning where the model is trained using labeled data. Labeled data is just the inputs labeled with the correct outputs. It would do this over and over again, gradually improving each time. For example, Rosenblatt ran experiments with the first perceptron, attempting to train it to recognize men from women. I also wanted to show this clip I found of the early iterations of AI, just so that you could see what it actually looked like.
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called.
He's using it to explore the mysterious problem of how the brain learns.
This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a beetle, the computer looks at facial features and hair outline and takes longer to learn what it's told by Dr. Taylor. Andrew Cruikshank's wig also causes a little heart-searching.
After training on lots of examples, it's given new faces it has never seen and is able to successfully distinguish male from female. It has learned.
Pretty cool, right? Let's zoom in on the internal design of a perceptron and how it determines classifications. You can think of each input unit in a perceptron as a digital version of a brain cell. It holds a number that reflects how active a physical feature is. Rosenblatt's perceptron started with a layer of input units, similar to how our senses detect basic features. Imagine those inputs are basic traits like hair length, height, and facial hair. Each person we show, the perceptron causes different input units to activate. One person might be tall with facial hair, another might be short with long hair. While the input units receive data directly from the images, the association units determine whether those inputs added together exceed a certain threshold. Each association unit is connected to a different, often overlapping subset of inputs, and each is responsible for responding to a specific combination of those inputs. For example, one unit might activate when it detects long hair and a soft jawline. Another might fire when it picks up on broad shoulders and a strong jawline. These patterns aren't labeled directly, but through repeated exposure, the perceptron starts treating them as meaningful clues. Once the association units process the incoming features, they pass their signals forward. Each association unit is either now firing or not, based on whether the inputs crossed the threshold. All of this leads to the final classification layer, called the output or response units, where a new weighted summation is performed to make the final classification. Let's say we have two outputs. One fires for man and the other fires for women. We already know that the output is determined by the weighted sum of its inputs. However, this is also known as a linear combination. In 2D, this can be represented as a line. So the perceptron can only learn to classify between two groups if it's possible to draw a linear boundary between those two groups. This is also known as being linearly separable.
So the perceptron can only learn to classify between two groups if it's possible to draw a linear boundary between those two groups. That's true for some datasets, but for other datasets, it's not possible. There's no linear boundary that separates the two groups perfectly. Even some simple functions aren't linearly separable. For example, the exclusive OR function, which outputs a 1 when exactly one of its inputs is 1, and outputs a 0 otherwise, isn't linearly separable. There's no line that separates the ones from the zeros. So given this limitation, how can we train computers to learn more complex patterns?
Like the video said, this started becoming a major problem when scientists started using the XOR function on the perceptron. The single layer perceptron could not handle complex data. It couldn't identify patterns where inputs overlapped or where relationships weren't linear. Graphically, XOR can't be separated by a straight line in 2 dimensions. There's no way to draw a simple boundary that separates all the ones and the zeros. That's why the single layer perceptron fails here. If we're using the XOR function in our man versus woman example, we would label man as 1. This would mean men are only labeled as 1 when only exactly one trait is masculine, and women would be labeled 0 when either both traits are feminine or both traits are masculine. But that leads to a weird situation. A tall person with short hair, 2 masculine traits, is labeled as a woman. This doesn't make intuitive sense. And even if we tried other combinations like a short woman with long hair or a tall man with long hair, it wouldn't change the fact that the outputs can't be separated by a straight line. The XOR problem remains not linearly separable. So what's the solution? How do we go beyond these limitations? What if we think in 3 dimensions instead of 2? If you add a 3rd dimension, like the x-axis, you can elevate the output, either 0 or 1, into a 3rd dimension. Now you have a 3D plot where inputs like 0, 0 and 1, 1 map to z equals 0. And inputs like 0, 1 and 1, 0 map to z equal 1. This makes them separable by a plane instead of a line. And this is exactly what multi-layer networks were designed to do. Transform input data into higher dimensions where complex patterns can become learnable. So what came next after perceptrons? That's what we'll cover next. In the next video, we'll break down the difference between traditional AI and modern AI and why multi-layer neural networks were needed to overcome limitations like XOR. We'll also learn how traditional AI systems that used fixed rules like knowledge-based systems compared to what we now call machine learning. Basically, the next video will be moving into the modern age. So if you have any questions or suggestions, leave a comment below and I will do my best to get back to it. Otherwise, I will see you in the next one. Bye.